Bismillahirrahmanirrahim. We'll start our lecture today about, we'll try to discuss two topics, two compartment model for IV bolus infusion and the IV infusion compartment model. We start with the two compartment model, IV bolus injection. In these drugs following these models, they observed following what we see in the graph here. That once some drugs, once a dose is taken by IV bolus injection, then we measure the plasma concentration versus time. Curve will not give a plot on semi-log paper. The curve will not give a straight line, but rather it will give the curve that you can see now. It has two different parts. Each has different slope. Okay? So when we think about it, what is the problem? Why here is not that giving straight line like in one compartment model? So then comes the interpretation, and proved also by other experimental methodologies. So observation here is log or ln CP versus time plot doesn't give a straight line. Okay. Then you see the slope here is larger. It means that there's a faster drop in drug plasma concentration with time. This initial phase compared to the last phase or the second phase. Okay. The initial phase shows a more rapid drop in plasma concentration before settling into a log linear fall in plasma concentration. So now when we comes to the explanation, we want to know why this happens or what is the cause of this phenomena. Then the logical interpretation is that in the initial phase, there is a distribution of the drug between. So it means that the first assumption that we mentioned before in one compartment model, that the distribution takes time. The drug takes time to reach to equilibrium between the free concentration in blood and free concentration in the tissues. Once the distribution is complete and the free drug concentration became in equilibrium, become equal in different tissues and blood blood compartment, then reach to the end of the distribution. From here, we'll start, we call it elimination phase or post-distribution phase, beta phase. Okay? So the first phase we call it distribution or alpha phase. Second, we call it post-distribution or beta phase. Okay, then to confirm this, simply if you give a drug, labeled drug, for example, where you can scan and you can identify from the image the areas that have luminescence indicate the presence of the drug, the areas of the body. So in two compartment model, this is what happens. For administration, you cannot place any drug in the body. Drug given by IV bolus injection. Immediately after administration, it can be traced in blood circulation, or we cannot, if you look at this image, we cannot see blood circulation. Now the blood circulation is evident. So because the drug is inside the blood circulation. What else? Some other organs like the heart, liver, and the lungs, brain also have the drug. This one indicates distribution of the drug immediately to these organs and blood. We call this the central compartment. Okay, so central compartment is not only the blood vessels, but it also includes the highly perfused organs. Highly perfused organs like liver, lungs, heart, kidneys as well. But once during distribution phase, then the drug will start to distribute into the peripheral tissues till distributing to all the body. And after reaching equilibrium, you can see that the color is homogeneous. It is same in all the body, almost homogeneous. So included means that there is distribution that happened to all the body. So now we want to sketch the model. We want to draw model and then to represent the pharmacokinetics of this kind of drugs. And we should include in the model all the processes that affect the concentration of drug in different compartments. So first thing we said, divide the body into two compartments: central compartment, including blood vessels and highly perfused tissues, not only blood vessels, and second compartment that includes the peripheral tissues. So we will draw two compartments: compartment 1 with a volume V1, and compartment 2 with volume V2. So these are the compartments. Then represent the injection by dose, and then this arrow. Didn't put here any rate constant because we give the injection, the bolus injection immediately, so there is no rate of administration, right? Immediately or instantaneously given. Then we have elimination rate constant, and elimination occurred from the central compartment. Okay? Blood vessel elimination occur either mostly in kidney or in liver, and these are supplied by blood. There is the drug, so it comes directly from central compartment. However, in this model we add two more constants, rate constants. One indicates the distribution of drug from central to peripheral compartment. We call it K1 to K12. K12 indicates from compartment 1 to compartment 2. The opposite will be other rate constant that indicates the back distribution of drug from peripheral into central compartment. Call it K21. So it is a two-way process. The distribution is a two-way process to keep equilibrium between the blood concentration in central and peripheral compartments. Okay? So assumptions of this model: body is not behaving as a single well-mixed compartment, unlike one compartment open model. The drugs distribute different rates to different body tissues. No instantaneous equilibrium between the drug and all the various tissues of the body, but it takes time. Plasma drug concentration declines by exponentially as the sum of two first-order processes, distribution and elimination. So in compartment open model, we log concentration versus time, find a linear line. So we say there is an exponential decrease. But here we have different slopes, so say by exponential decrease. Sum of the change of the concentration of the plasma is the result of the sum of two first-order processes. It is affected now by distribution and elimination. In one compartment of the model, it does not include the distribution or model because it happens immediately. It doesn't have any time to complete. There is no rate, so it has no effect. Didn't observe it. It doesn't have effect on the drug plasma concentration. As we mentioned, central compartment consists of highly perfused tissues and drug is eliminated and distributed to tissue compartments from the central compartment. So if I ask you, drug is eliminated from where? From central compartment. Then distribution happens initially from where? Initially, when you give the injection into the central compartment, then distribution happens in this direction, K1, K1 to from central to peripheral compartment. However, after distribution is complete and when elimination is going on, keep the equilibrium, then The other direction will be dominant, as we will see here. So as you see, when we give the injection, all the drug in the central compartment at the beginning. So the prominent is the direction of 1 to 2. To reach equilibrium, finish the distribution phase. Here, got equilibrium between the drug concentration in central and peripheral compartments. Then elimination is the only thing that will affect the drug concentration in the central compartment. So the drug is decreasing in compartment 1. So compensated for the time by equal, but an amount of drug from compartment 2 to keep the equilibrium persisting. This happens till infinity, till the drug is completely eliminated. Okay, so after this during elimination phase, the direction from 2 to 1 is to meeting. So if we look at the drug concentration versus time in plasma and in tissues, plasma is the graph that we showed. The drug has by exponential decrease. So there is a decrease in concentration faster in the distribution phase initially, and then the slope will become less in the beta phase. There are processes will be in beta phase, elimination from central compartment and back, distribution from compartment 2 into compartment 1. But if we monitor the drug concentration in tissues, time 0 there is no drug in tissues, and there is fast increase due to the distribution. Once distribution phase completed, then the drug will be decreased in the tissues because of distribution and elimination, because it will be back distributed to the central compartment. So the concentration will keep decreasing till reaching almost 0. Okay. So we make a rapid comparison based on the information that we mentioned between distribution phase and elimination phase. When it comes to timing, distribution phase occurs first. It happens shortly after ejection. But elimination phase occurs later on, once there is equilibrium between the fraction of drug in the peripheral and central compartment. In distribution phase, most of the dose is in compartment 1. So opposite will be here. There will be a smaller fraction of the dose in the tissue, peripheral tissue, till reach equilibrium. Okay. Then when we talk about drug net movement, there is net movement in the distribution phase from 1 to 2. Means the ratio is changing. When I'm talking about net movement, I didn't say movement only. You have to pay attention for this. I didn't say drug movement, because drug movement happening between the two compartments, as we explained all the time during alpha and beta phase. Here I'm talking about net movement. When I say net movement, I mean there will be a change in the ratio between the drug in compartment 1 and compartment 2. So yes, in the distribution phase, ratio is changing. Compartment 1 to compartment 2 is higher, and then keeping distributing to compartment 2, so ratio is decreasing, right? So we call this is the net movement. But here, after the equilibrium established, there is no net movement. There is equilibrium going on when the drug is decreasing from compartment 1 because of elimination. There will be a back distribution from compartment 2 to keep the ratio fixed. So there's no net movement of drug between compartments in elimination. So be careful. Pay attention for the difference between when I say drug movement and when I say drug net movement. When I say net movement means a movement of drug in any direction, but in a way that will change the ratio between drug in compartment 1 and drug in compartment. As you see, when we saw in the graph, the slope is different. Higher slope in the initial phase, the alpha phase means faster decline. The fast fall in drug concentration compartment 1 due to drug distribution into tissue compartment. But in initial phase, the drug decrease will be slower and will be parallel both compartments. So we saw this curve, drug decrease in the phase is parallel. They are decreasing by the same rate. Compartment 1 and compartment 2 in plasma and tissues. Okay, and the slope is smaller, means there is slower increase in the level of drug. So from these slopes, we can conclude that the rate of distribution is faster than the rate of elimination. That's why the slope is different. Okay? So when it comes to the kinetics, the kinetics appear to follow one compartment model in the elimination phase. It will be in the second phase will be like one compartment model. If we just look at this part alone, okay, the beta phase, so it is one line, straight line with one slope. So now it looks like open beta phase. Kinetics in the elimination phase of the phase appears to follow one compartment model. Which drug elimination is a first order process described by beta. Actually, beta doesn't represent only Ke, but it represents both two processes going on here, Ke and K21. So when it comes to why drugs are different in terms of distribution into the tissues, there are many factors that may affect this. Number one, blood flow to the tissues. So in the diagram, we saw that the highly perfused tissues will have rapid equilibrium. They are considered part of the central compartment. Second thing is the permeability of the drug into the tissues. You know that drugs with high lipid solubility will distribute more to the peripheral tissues. While drugs with aqueous solubility, they distribute slower. Partitioning also depends on the partition coefficient. So there will be partitioning between the tissues and blood, the drug. So drugs with high partition coefficient, they usually will have rapid or more distribution into the tissues. Also, the capacity of the tissues to accumulate drug, different tissues has different capacities. That's why when you study drugs, you can find that some are more distributed to the fat, some of adipose tissue, some have higher concentrations in the heart, and so on. They have different affinities to different tissues. Also, the effect of disease on these processes. There is a disease that will change, for example, cause edema, and the patient will have more body water, then it will affect the volume of distribution of the hydrophilic drugs. Okay? Obese patients will have more volume of distribution for lipophilic drugs and so on. Okay. We go to the model equations. The model equations are somewhat complex compared to one compartment open model, because now we don't have only one process that will affect or cause the change in drug concentration. In one compartment open model, elimination only, so the equation was simple, containing only the elimination rate constant. But here we have two processes, distribution and elimination, and we have three rate constant, K elimination, K21 or K21 and K12. So the equation will be more complex. This is the main equation we have to pay attention for, and we will use. This one indicates that concentration of drug in plasma equal to, have two intercepts here. So we say by exponential, we have two intercepts, we have two slopes. So one intercept we call it A, the other intercept is B. One slope is alpha and the other slope is beta, and both of them multiplied by time. So, and then here the exponent, so exponential by exponential decrease. We have two exponents here. Okay. So A multiplied by exponent of negative alpha multiplied by time plus B multiplied by exponent of negative beta multiplied by time. This is the main equation you have to look at. And if you want to calculate the drug concentration in any compartment, either in the central, equals Cp, or in the tissue, Ct, you have to divide the drug amount in this compartment, so dP or dt, by the volume of this compartment. So here Vp is the volume of the central compartment, Pt is the volume of the tissue compartment. Okay? If you want to replace these equations alpha and beta, then you have to replace with A21, A12, and also K10, we call it, or K elimination. So you will get more complicated equations. We will not apply these two equations much. It has no benefit almost in clinical practice, just to do it, but we don't need to stop too much by it. Then here, the most important also, we have to know that we have two different half-lives. We have half-life for the alpha phase, and we have half-life for the beta phase. So same thing, when we divide the half-life by the slope in one compartment open model. So for each phase, divide, if you want to calculate the half-life, we divide the 0.693 by the slope in case of one compartment open model. Same thing here. Also, when you want to calculate the half-life of distribution phase, you divide the 0.693 by its slope, which is alpha. And then you also, when you want to calculate the half-life of the beta phase, you divide the 0.693 by the slope of that phase, which is beta. So experimentally now, or practically, we want to calculate the pharmacokinetic parameters of these drugs. How do we calculate them? The parameter determination will be using a method, we call it the method of residuals. So we call it feathering, peeling, or stripping method. Why we call it like this, residuals, stripping, or peeling, or feathering? Because we have one curve. Okay, we have one curve, one line. We have one line. This has two by exponential degrees, showing by exponential degrees. It is a sum, as we said, of two processes, distribution and elimination. We separate it into the mono exponential components. Okay, so we call it like this because this process allows separation of mono exponential constituents of by exponential plot of plasma concentration against time. How do we do it? As I explained to you before in the previous lecture, when we do this kind of pharmacokinetic research, the methodology usually is to give a dose of the drug and take plasma concentrations, and measure plasma concentrations in blood samples taken different time intervals. So the net result, you will have a plot of blood level versus time, and we make it on a semi-log paper. So we plot lung concentration versus time. So we look at the line after this. If you find that it gives a straight line, then you can say this drug is following one compartment open model. If you find that it is giving a line that has two phases with two different slopes, then we say the drug is following two compartment open model. Okay, so this point is clear. Practically, how to identify the model that the drug is following, then by doing kind of kinetic study. You give a certain dose of the drug, you collect blood samples, you measure the concentration, plot the concentration in blood versus time, and then we look at the shape of the curve on a semi-log paper. So when we plot lung concentrations versus time on a normal paper, normal graph paper, and then see the shape. If it gives a straight line, one straight line, then we say this drug follows one compartment open model. If it gives this kind of lines by exponential, then we say this is a two compartment open model kinetics. Okay, so how to know, make this method of residuals. When it comes to residuals, the slope, if we calculate, will give us beta value, and the intercept will give us b value. So the b intercept is for this extrapolated surface. Okay. So here will be the value of b. Okay. So where are the residuals now? When we say residuals, it means we want to calculate some differences. So you have a new curve. So you have two values of y for the same x. For example, at 1 hour, intercept here is different from intercept, right? At 1 hour, the value is different. Have a higher value and smaller. We minus, only we minus in this part that is, we call it alpha phase. Alpha phase, there are two processes going on. There is distribution and there is elimination. Want to remove, minus them from each other. So this line represents elimination. This line represents distribution plus elimination. So when we say distribution plus elimination, this is the alpha phase. Minus elimination, it will give you only the distribution. So the result will indicate the values that represent the distribution process only. So we calculate the difference and then we plot these points again. We make a new line. This line will have slope, we call it alpha, and then we'll have intercept, we call it A. Then by this way, you can get the equation model and then you can predict concentration of the drug after the administration. Okay. So if we're using semilog paper, then we have to always, as we mentioned previously, to use the factor 2.3 to convert from log to ln, because kinetic calculations always based on ln concentration versus time, not log. Here we use the log value, so convert it to. Okay. If you are plotting ln concentration versus time, then you don't need to use this factor for conversion. Just measure the slope, calculate the slope immediately, and change the sign from negative to positive. Okay, this is how we do. So as I mentioned to you, the model we didn't mention alpha and beta. The model we have K12 distribution from rate of rate constant for distribution from compartment 1 to compartment 2. K21 is the rate constant for distribution from compartment 2 to 1. And K10, this is the elimination rate constant. It's 10 because 1 to 0 means elimination happened from central compartment, compartment 1 into out, in nothing. Okay? Available anymore, so 0. So say K10. So alpha and beta together, they are equal to, or they express the three rate constant together. Alpha times beta is equal to K21 times. From this, you can modify the equations to calculate K21, K10, and K12. So if you see this equation, K10 will be equal to alpha times beta divided by K21. K21 equal to alpha times beta divided by 10. So here, this one. If you observe this equation, K21 is equal to this value, right? So K10 is equal to alpha times beta divided by K21, means alpha times beta divided by this value. value you invert because you divide by, so A plus B will come to the numerator, and then A beta beta uh, B alpha will come in the denominator. So is it clear up till this point? You can hear me? My voice clear? Oh, okay. So we continue. How to calculate the volume of distribution of each compartment. These are the equations. Central compartment, we call it VP or VC. VP is mostly used, so you just make correction. Volume of central compartment is apparent volume of central. VP is apparent volume of distribution of central compartment. Apparent volume of central compartment. How can you calculate it? This represents the ratio between dose and concentration at time zero. Because at time zero, all the drug in the central compartment. So we use the concentration at time zero, and we are using the we are indicating the amount of drug that is only stay in the central compartment. Okay, this is one thing. So it is equal to the dose divided by CP naught. Actually, CP naught is the sum of the two intercepts A and B. Okay, and then if you remember, another way to calculate is by dividing dose by AC. This represents clearance, if you remember. Dose by AC is clearance. So we are dividing clearance by elimination rate constant. So we know that elimination rate constant equal to clearance times clearance equal to volume distribution times elimination rate constant. If you want to calculate any of the two, divide the dose by the other one. Okay? So this one can be used to calculate the drug concentration immediately post-dosing. From the volume of central compartment, you can expect what will be the CP naught. If you know this volume, you know the dose you give, then you can expect how much will be the CP naught. And this is useful in calculation of drug clearance as well, because if you know it, okay, then and you know K10, then you calculate the clearance, which is used by AUC. Okay, when it comes to the volume distribution of the drug in the body, beta during beta phase, this not for the peripheral tissue only, this one for the equilibrium for both central and peripheral compartments. So to calculate it, then V beta equal to dose divided by beta times AUC, or equal to the volume of distribution of central compartment times elimination rate constant divided by beta. Clearance divided by clearance will replace the dose divided by AUC. So this is not the volume of peripheral tissues. This is the volume of distribution in all the body at beta phase. So during this phase, drug will be in both tissue and central compartment. If you want to calculate AUC, the same equation we know before, you can use trapezoidal rule. AUC equal to AUC from 0 to 3p last measured concentration plus the AUC from 3p last till infinity. Another way mathematically to calculate is divide each the intercept of each phase divided by the slope of that phase. A divided by alpha plus B divided by delta. We can calculate also the volume steady state, volume distribution at steady state when the drug is, we could say, the amount of drug in the body at steady state is after 3 or 5 half-lives. This time there is usually equilibrium between the drug and the drug in the central compartment, and also when we reach steady state, then concentration is stable. This one after repeated administration. We take the drug several times for a period of 3 to half lives, and then the drug's concentration will almost be fixed. So in this case, there is no decrease in the concentration because the rate of administration equal to rate of elimination. So this is the equation to calculate. Calculate it either from the volume of central compartment or volume of distribution in the body at beta phase. Okay, we will leave this example. You can explain quickly, but we will practice it in the practical later on. Okay? So here, for this set of data, we have concentration in plasma versus time. Then we want to describe the pharmacokinetics of this drug and calculate drug pharmacokinetic parameters. So as we say, the first thing is to plot. Then we see if this is a straight line or there is a by exponential decrease in the concentration. So this is the trend line, the straight line. As you see that this one is not a straight line. So when you describe the pharmacokinetics, you cannot say this is one compartment model, but this is a two compartment. The drug is following two compartment kinetics. Okay. And then the concentrations here is from 17.5. So we'll plot it later. This plot is not accurate. Suppose that the value is not increase more than here. So we will plot it again in the practical, then we'll see. So if you find that the line is gives straight line, then we say the drug is following one compartment open model. If it gives the line same like what we saw in this lecture, like 2 pi exponential, then we say two compartment open model. How we are going to calculate the pharmacokinetic parameters for two compartment open model? As we mentioned, we will use the residual method. So what is the residual method? We have to like this. Another set of data. We'll have the plot. Okay. Have the time versus concentration. Okay. So you look at first phase where slope will change. So I take the first part, first points. Then the first points. Second thing is I take the terminal phase. I will take a straight. Okay. Okay. So suppose that you have exponential decrease like this. So the first thing is to extend, like extrapolate terminal phase. And then now you have two lines. Then you at each time point determine how much the y value. Y value for the back extrapolated, we call it CP late. Call it CP late. Call it CP late. So when I back extrapolated at certain time, value for the back extrapolated certain value, I put it here. Of course, it will be less because the y here is higher. So at time 0, I have the b value. I have the CP node value. I put here the CP node time 0, for example. And here I put b value. In 5 hours, the value of CP was this value, but in CP late, the extrapolated part, it was a lower value. I put the value. Same at 1 hour. But how much is the value of y in the back extrapolated one? I put in the table. And I calculate the residuals. Residual is difference between them. CP minus CP. How much? Then you plot them at 0.5 hours. Once the value should be 20. Then by 20, put a point. Then another value at 1 hour, it was 13. I put a point. At 1.5 hours, it was 4.5. I put a point. Then I connect them. I extend the line. Intercept will be alpha or beta, be alpha. Will be A or B, will be A. Okay? So this is what I did. I connected the points here. So I got this intercept is A. The slope of this line is alpha. If I want to calculate the half-life of this alpha phase, then I divide 0.693 by the alpha by 1.046. If I want to calculate the VP, then I just follow the equation. I compensate the values. You want to calculate VP can be CP node divided by can be dose divided by CP node. CP node is the total of A and B. So B calculated before. Come back extrapolation of the linear phase, the second phase, okay, the beta phase. Extrapolate, I calculated B. Its slope is the half-life is divide the 0.693 by beta value. Okay. So now I have A and B value, I have alpha and beta. So the equation that represent will be equal to A exponent negative to the power A times exponent negative to the power negative alpha times t plus B multiplied by the exponent of negative beta multiplied by t. We just have a 5 minutes break and then we will continue other topic. So now we've discussed the one compartment open model, intravenous infusion. And intravenous infusion is unlike the IV bolus, not given instantaneously. As you know, you can see in the photo here, there's a bottle. There is a small part appearing from the bottle, and there is a line. The line will end into a needle that is inserted into the vein, and the drug is dissolved in the IV fluid, and then administration is gradually. There is dripping rate. Okay, so there is a rate of administration. So we want to represent this model, we have to add another rate now. There is a rate of administration because administration is not instantaneous. Okay. So there are different types of infusion. There is what we call it continuous infusion, and there is a intermittent infusion. So what is the difference between them? Continuous infusion is for drugs usually that very short half-life, like nitroglycerin, for example. Half-life is about less than 1 minute from this value. So this one will be eliminated very quickly. If you stop the drug, there will be no more effect, a very short time. So to keep the effect, you have to keep administering the drug all the time. As long as the drug is dripping to the vein, then the effect is going on. So when we want to stop the effect of the drug, we just stop the line, stop the dripping rate, the dripping of the IV fluid. So then finish the administration. We call this one continuous IV infusion. But some other drugs be administered, for example, 3 times a day, every 8 hours, but the dose will be given as short infusion. We call it intermittent IV infusion. The instructions for use will be to give this drug by, for example, as a 30 minutes infusion or as 1 hour infusion. It means that you have certain volume of drug in an IV fluid. I mean, how much IV fluid you need to drip, for example, 0.5 liter. You have to program the pump or you adjust the dripping rate so that this 0.5 liter will finish in 1 hour if you want it to be 1 hour. And then the drug is given, it is inside the body, will be eliminated gradually till after 8 hours, probably, but from administration time, the concentration is low, then we need to give another dose. How to give again by short infusion, 1 hour time. So on. This one we call it intermittent IV infusion. So intermittent IV infusion, the infusion of a volume of fluid or medication over a set period of time. We set this period of time, okay, and at a prescribed interval, and then stop until the next dose is required. So we set this period of time, for example, as I mentioned, to be 30 minutes infusion. So infuse over 30 minutes, finish all the dose given in 30 minutes. Then the frequency is every 8 hours. Then after 8 hours from starting the first infusion, from starting, we calculate the interval from starting the first infusion. Starting, again, I say from starting the first infusion. Then after 8 hours from the starting of the first infusion, we start another infusion. This is the dosage interval. Okay. This one used when drugs cannot be given by rapid IV injection. So now we want to represent the model. We said one compartment model. So one compartment, then we put one square or one circle represents the volume of the compartment. So what do we mean by one compartment? Means the drug distributes immediately into tissues, and there is equilibrium between drug and tissues immediately. So here in the model, we don't have any rate constant representing distribution. Same like one compartment model IV bolus, the drug is eliminated central from this compartment. So there is rate of elimination, KE, or there is clearance. But unlike IV bolus here, because there is rate of administration, then in the compartment, there must be a rate constant representing the administration rate. That so the difference between infusion and IV bolus in one compartment model is just only that we add one term that represents the rate of administration. So if you look at this model, if I ask you what are the factors that affect the amount of drug in the body and similarly the concentration of drug in the body, okay, or in the plasma, okay. Then you have two factors now, rate of administration and rate of elimination. Amount that is remaining or the concentration in the plasma will be the net result of two factors, one adding and one removing, right? So it will be this minus this, administration minus elimination. Okay, so if I ask, if we are giving intravenous infusion, continuous intravenous infusion, what happens to the drug plasma concentration? At time 0, before we start, just about to start the infusion, there's no drug in the body, so the concentration at time 0 is 0. So if you give drug infusion, then the concentration. See, just follow this dotted line. This one represents the IV infusion, constant IV infusion. Constant means we fix the rate. We are not changing the rate. Set the dripping rate to be, for example, 1 ml per minute. That's all constant. It continues. So the drug concentration will keep increasing, keep increasing. Okay. Will it increase to infinity? No. We say in this compartment assumptions that the elimination is first order. And we said what's the meaning of first order means that there is a factor that elimination depends on. Elimination is concentration dependent. The rate of elimination is concentration dependent. The higher the concentration, the higher the rate of elimination. Isn't it? Remember. So as the concentration is keeping increasing, the rate of elimination also is keeping increasing. So the slope is changing here. The rate of increase is not the same, if you see. Isn't it? So the rate of administration is fixed, constant, by giving the drug by certain rate, not changing. But which rate is changing? The rate of elimination. So I go back to the model. We said the amount of drug in the body equal to rate of administration, affected by the difference between rate of administration and rate of elimination. The beginning rate of elimination is rate of administration is higher than rate of elimination. So there is accumulation of drug. This difference is decreasing with time because the rate of elimination is increasing with the increase of amount of drug in the body and the concentration in plasma. Till we reach a certain point when rate of elimination is equal to the rate of administration, then we call this one a steady state. If the two rates will be equal, N equal to out, what happens to the amount of drug in the body? Increase, or become stable? Becomes stable. What happens to concentration in plasma? Becomes stable. So we call it steady. Steady means stable, doesn't change. Steady state is a condition achieved after multiple doses or continuous administration of drug. It can also happen with IV bolus. This is IV bolus, this line, multiple IV. Give one IV bolus, give certain CP node, certain Cmin. Give another one, it will increase further. Okay? Because it will add up. It will add up, right? So keeping increasing, Cmax and Cmin keeping increasing. Till the rate of administration will equal to the rate of elimination, then they will move in the same range. They will not change after this. This usually happens after 5 half-lives. Ideally, as we mentioned last time, for 7 half-lives. Almost 99, 98 or 96%, you reach to the steady state concentration after 5 half-lives. Drug concentration became stable. And this happens when the rate of elimination become equal to the rate of administration. Rate of administration zero order process, fixed, doesn't change, but elimination, as we mentioned, is the first order process. The rate of elimination increase as long as the concentration of drug in plasma keeping increasing, and to reach a level that it will become equal to the rate of administration, then that concentration will not change any. And to reach steady state, as we mentioned, 99% after about 6.65 half-lives. So practically, for practical reasons, about half-lives means that the concentration reached about 96% of the steady state concentration. So you can say it reached steady state. You can do calculations at this time using steady state equations. It will result in minimal error. It will not affect. Okay. So for steady state, factors affecting, as we mentioned, rate of elimination, rate of administration, the change of the amount of drug in the body with time is net result of rate of administration minus rate of elimination. You remember the equation before, rate of elimination equal to K, elimination rate constant, times the amount of drug in the body, or equal to K times VD times CP. Okay. So by integration, we get this equation, amount of drug in the body at certain time equal to rate of administration. This is rate of administration is the rate of infusion. So in practice, you see in the data, how much was the infusion rate? Drug, how many milligram? If you say rate of administration of drug, then divide the dose milligrams, for example, per minute or per hour, okay, per time. Rate is always the amount per time divided by elimination rate times 1 minus e to the exponent kt. If you look at this equation, anything in the top denominator is proportional to y that we need to calculate. Anything down is proportional, inversely proportional. So here you increase the rate of administration, the rate of infusion, then you increase the amount of drug in the body. If elimination increased, rate of elimination, if the elimination rate constant increased, then the amount will be decreased. So the same example I gave, if you want to compare two patients, we have taken the same dose, the same infusion rate, but one of them has better renal function and the drug is eliminated by renal route. So then if E is higher, then they will result in less amount of drug in the body and less concentration of drug in plasma. Other patients that have renal function problem, impairment of renal function, K is less, then the amount of drug in the body and the concentration in plasma will be higher. I replace this D by volume of this by D is equal to Cp times Vd. So times Cp times Vd, and then you want to transfer Vd to volume distribution to the other side of the equation, then you divide by it. So if you want to calculate the concentration of drug in plasma at any time, it will be equal to K0 diffusion rate, and use 0 here because it is 0 order process rate, divided by K times Vd times 1 minus e to the power negative K. The question is now, if you look at this equation, this is fraction, right? This is not an integer or whole number. This is a fraction. So you multiply this amount by 1 minus fraction. Okay. Then with time, what does happen? With time, what happens to this fraction? K is fixed, right? But E is increasing. So this one will be equal to 1 divided by e to the power kt. K keeping increasing, so the denominator increasing. So the fraction becomes smaller, smaller till approaching 0. This one happens at steady state. This fraction equal to 0. So 1 minus 0 is 1. So at steady state, this only will be the equation for concentration in plasma. Before steady state, how is the concentration? More or less? Are keeping minusing value from 1. 1 minus any value, 1 minus 0.1, minus 0.2, 1 minus 0.3, 1 minus 0.4 is a fraction. You are multiplying this by fraction. So this part alone is the steady state concentration of drug in plasma multiplied by fraction. So it is less, same as we saw in the graph. Keeping increasing at steady state, this fraction we minus from 1 is 0. So we'll get a higher. So this is the equation at steady state. At steady state, we say infusion rate is equal to elimination rate. So, you know, 0 is equal to clearance times CSS. This is CPSS, concentration plasma at steady state. Or you can say, if you remember, the clearance is KE as the volume of distribution, right? Clearance is KE times volume of distribution. So we can say that CSS can be equal to K node divided by K times VD. Look at this part, look at this equation. It represents this part of the equation. So this means that I can ask you a question now. Can I use this equation for all the time, either C at steady state or non-steady state? You write for me the answer, can or no? Can I use this equation to calculate concentration in plasma at steady state? Can or no? Of course, can. Because value of this one will be almost 0. So the 1 minus 0 is 1. Then it will give me the same value. So why I use this one, not this one? I want to make life easy. No need to put big equation. While you are practicing in the ward, you want to do quick calculations. You can just use little terms in the equation, calculate the concentration at steady state using this simple. Okay, let's just practice an example. A drug was administered by IV infusion rate of 60 milligram per hour. Calculate the time required to reach a therapeutic concentration of 10 milligram per liter. Knowing that the inhalation rate constant is 0.17 and the volume distribution is 25. Now here we didn't mention anything about steady state. Just telling that we are giving infusion at certain rate. Then we know that once we start the infusion, the concentrate will keep the drug plasma concentration will keep increasing. So we want to know while the infusion is going on, what time to reach the value of 10 milligram per liter concentration. So here I don't use the steady state equation. I have to use the full equation. So the unknown thing is the time. And all the other values are known. Concentration Cp is 10. A is given, initial rate constant. Volume distribution is given 25 liter. Fusion rate is milligram per hour. Before you start answering, you have to be sure that all the units are same. Here, milligram per hour, here should be the K should be hour. They give you the initial rate in milligram per minute, for example, then microgram per minute, then you have to convert minute to hours to be same like K. Concentration milligram per liter. Volume distribution same liter. I'll give you concentration, for example, milligram per ml, and you use the same value equation while your volume distribution in liters. All should be the same units. Volumes should have the same units. Time should have the same unit. Amount should have the same unit. You cannot use concentration value in microgram while your infusion rate is in milligram, for example. Okay, this is the first thing you have to check before you start answering. Just replace, and then I modify the equation. Okay, I move this fraction to the other side. I invert, and numerator will be denominator, and vice versa. So you have 1. So I move 1 to the other side, this part to the other side. Change the sign. This one will be positive there, this one will be negative here. So E exponent of negative 17 times t will be equal to 1 minus 708. 1 minus 708 will give you how much? 292, right? 0.292. So this one alone is 0.29. So how to get this one? Make antilon. So you have to make antilon of you have 0.292. Okay. To make antilon for this value, you get the negative 0.17 times t. So when you get negative the antilon of this value 0.292, then it will be equal to a negative 17 times t. So t will be antilon of 0.292 divided by 0.7. The net result will be is 7.24. This means that after 7 hours of continuous administration of the drug at this infusion rate, concentration in plasma will reach 10 milligram per liter. Other examples. A drug, vasopressor drug, has a volume of distribution 12 liters. K value is 0.115. Steady state plasma concentration is desired in microgram per ml. So they want you to calculate the dose or infusion rate here, infusion rate that needed to maintain this concentration. Number one, when we look at the units, here volume distribution in liter, but concentration in microgram per. We know that microgram per mil is equal to milligram per liter. So we assume this one milligram per liter. Okay, then the units will be same. So when we calculate the infusion rate, it will be in milligrams per hour because K is hour to the power negative 1. So since we are talking about steady state, we want the desired steady state concentration, the desired infusion rate to reach a steady state concentration. Then we have to use steady state equation. Life easy. So concentration at steady state in plasma, we can write it CPSS equal to infusion rate divided by K times volume distribution. Unknown is the infusion rate. So infusion rate equal to CPSS times K times D. So equal to milligram per liter. We unify the units here. Times 0.115 times 12 liters. Okay. Then you will get 13.8. Your unit will be milligram per hour. The same unit of the K. 13.8 milligram per hour. Other problem, drug was administered by IV infusion at a rate of 14 milligram per hour. Calculate the steady state concentration, knowing that the elimination rate constant is 0.125 or to the power minus 1 and volume distribution is 14 liter. So we look at the units, milligram hour, volume distribution is not given here, given 14 liter. Okay. So they want, this is required to calculate the steady state concentration. Okay. So steady state concentration will be in milligram per liter, milligram per. So calculate steady state concentration. So I use this equation. Steady state concentration equals to infusion rate 14 milligram per hour divided by elimination rate constant times volume of distribution. So simple. Just replace values equal to 14 divided by 1.125 times 14. So get 8, and units will be milligram per hour. Okay. Another example. Patient was given antibiotic by constant IV infusion at a rate of 2 milligram per hour. At the end of 2 days, serum drug concentration is 10 milligram per liter. Calculate the total body clearance. Clearance is simply K times volume of distribution. So from this one, you probably calculate the number one K. Here, K half-life is given, not K directly, so we know the equation. Comproved open model. K is 0.693 divided by T half, 693 divided by 6 hours, so 1155 hour to the power minus. The meaning is to get the volume of distribution to be able to calculate clearance. We are talking about at the end of 2 days, the serum drug concentration is whatever. I didn't mention is it a steady state or no, but we can know from the half-life. Half-life is how many hours? 6 hours. How long does it take to reach a steady state? We say practically we use the value 5 half-lives. So 6 hours times 5 half-lives equal to 30 hours. The infusion continued for 2 days. 2 days, definitely more than 30 hours. The time to reach the state is 30 hours. We took 48 hours, so definitely it is a steady state. And the other way, you can calculate the how many half-lives now. 48 hours, the 2 days, divided by the half-life 6 means already 8 half-lives. 8 half-lives. Continuous administration means already reached steady state. Right? So we can calculate the steady state. We can use the steady state equation directly. K infusion rate equal to clearance times CSS. So this one way directly we use this for. So infusion rate is 2 milligram per hour. Clearance unknown. Concentration here is a steady state concentration 10. So clearance equal to divided by 10. Other way, if you don't remember this equation, you still remember only the simple form that is node equal to Ke times Vd times CSS. You can calculate the volume of distribution from this equation, and then we multiply by K. Okay. Another example to practice: a drug was administered by continuous IV infusion at a rate of K0 0 equal to 60 milligram per hour. Calculate the steady state concentration and time to reach steady state, knowing that K equal to 0.24 4 to the power minus 1 Vd equal to 24 liters per hour. So your concentration will be in milligram per liter. Units are okay, we can go on and calculate. So we'll use steady state equation. CSS equal to K0 divided by K times Vd. Just replace the values: 60 milligram per hour, the K0, 0.24 the initial rate constant, 25 is the volume distribution, then steady state concentration is 10 milligram per liter. To calculate the time to reach steady state, you need to know the T half. Calculate the time to reach steady state, you need to know the T half. T half can be calculated from value of K. So T half is equal to 0.693 divided by K, 0.693 divided by 24, so 2.89 hours. How many half-lives to reach steady state? We said 5, or you want to say 6.65, okay also. So you can multiply the time T half by, if for example here 6.65 to reach 99, I mentioned I specified to reach 99% of the state concentration. 6.65 half-life, so I multiply by the half-life, equal to 19 hours. Okay, so after 19 hours we reach the steady state concentration. Now we want to know something else, is how to measure the concentration after we stop the fusion. After we stop the infusion. So we know that this is a one compartment open model. So if there is no administration anymore, we stop the infusion, then what equation will apply? One compartment or two compartment open model? What do you think? Which equation will use, one or two compartment open model? No more rate of administration, then there's no K0, then we just follow the one compartment open model for IV bolus. Okay. So in this case, after we stop, for example, we stopped here before reaching steady state, then the concentration will be equal to the last concentration while the infusion is going on at this time, B, multiplied by the exponent of negative 80. That's all. If we continue till steady state, then we multiply the steady state concentration by the exponent of negative 80. Okay. So once IV infusion stops, the drug concentration will decrease exponentially based on the initial rate constant. So the equation will be T will be equal to blast concentration from the infusion times E the power negative A E. The most important here, what kind of T is it? How to calculate this T? So this T is time since we stopped the infusion. Time since we stopped the infusion. The time since we started the infusion. You want to calculate this concentration, then the time will be since you started the infusion. But you want to calculate concentration here, then it is equation for calculation based on IV infusion using the time since we started the infusion times E to the power times exponent of negative KT, and here there will be the time since we stopped the infusion. We practice with example. A drug was infused for 6 hours at rate of 2 milligram per hour. Calculate the concentration of the drug in the body 2 hours after cessation of the infusion. The infusion continued for 6 hours. And then you want to calculate the concentration 2 hours later. So it will be two steps calculation. Number one is to calculate concentration at the end of the infusion, 6 hours period, using the equation steady state here. Concentration at 6 hours equal to infusion rate divided by K times volume distribution multiplied by this value between the brackets. Time here is the infusion time, the 6 hours. So equal to infusion rate 2 milligram per hour times 1 minus exponent of negative A 0.01 times the time of the infusion. Because here I want to calculate first the concentration at the end of the infusion, at the end of this 6 hours period, divided by K times V equal to 1.1647. What will happen to this concentration? 2 hours after I stop the infusion will decrease more. Decrease by which rate? Exponentially. Multiply it. Same equation for IV bolus that we used. C2 equal to C1 times exponent of negative Kt. So Cp2 equals Cp1 exponent times exponent of negative Kt. Time here is after we stop, 2 hours. So it is equal to this value at the end of the infusion times exponent of negative K times 2 hours. So will be more or less. Will be more or less. Will be lesser. 1.14 milligram per liter. Let's look at the equation and what are the factors that affect the drug concentration. CSS equal to K naught divided by clearance or K0 divided by clearance or K0 divided by KVD. Anything on top, increase the concentration. So increase by increasing the infusion rate. Anything at the bottom, decrease the concentration. So increasing clearance will decrease concentration. Increasing the volume distribution, increasing K will decrease the concentration of drug in plasma at steady state. So you give both of them the same infusion rate, but they are different in two patients. You give them same drug at the same infusion rate. There are difference in clearance values or volume distribution values. The one that have higher VD have less concentration. The one that have higher elimination rate constant will have less concentration. Both of them are same in terms of elimination and volume distribution, but you give different infusion rates. The one that gets higher infusion rate, you will achieve in him a higher concentration at steady state. Okay. Now another concept we need to know that in clinical practice, sometimes before they start the infusion, they will give a loading dose. So what is the purpose of the loading dose? The concept is you'll take about 5 half-lives to reach 96% of the steady state concentration. Sometimes for some drugs that have long half-life, this will be a long time, maybe 2 days, to reach the concentration you desire. So you don't want to wait for 2 days to reach this level of drug that will give good effect. So you want to achieve it immediately. So they may give fast infusion, fast short infusion, or sometimes IV bolus, but mostly fast infusion to achieve CS, the desired steady state concentration immediately. And then they continue the infusion rate that will maintain it. So loading dose are utilized where rapid achievement of therapeutic levels is desired without waiting for life to half-lives. Loading dose will be equal to the amount of drug necessary to quickly achieve the therapeutic levels in the target tissues. So how to calculate the loading dose? Same like an IV bolus. Loading dose is equal to concentration times BD. The desired concentration is the steady state concentration I want to achieve. So it is equal to steady state concentration times VD. Okay? And if we use the equation of steady state, the infusion rate equal to that steady state concentration equal to infusion rate divided by KVD. So loading dose will be equal to this concentration times D. Replace the concentration by this one, this fraction. Okay, so the loading dose equal to, instead of CSS, we put this value. So VD eliminated with VD in the numerator and denominator, then You can estimate the loading dose from a very simple equation, infusion rate divided by K. So instead of multiplying CSS by VD, if you don't know VD, mind, you know initial rate constant, divide the infusion rate that you will use by the initial rate constant. This is another equation. So use either this or this is correct. Okay. So what happens here? You immediately reach to steady state concentration. So the rate of elimination will increase also immediately. First order kinetics, right? So the rate of elimination immediately will be equal to the diffusion rate. So what happens to the concentration? Stable, will not change. Will be kept at the same level. This practice, calculate for the previous example, calculate the required loading dose. Previous example number 6. Here, K was 0.01. Diffusion rate was milligram per hour. It's asking to calculate the loading dose, so I just divide 2 by 0.01. Diffusion rate divided by, oh sorry, should be example 5. Okay. So I divide 60 by 0.24. Divide 60 by 0.24, so equal to 150 milligrams. So I should give a loading dose of 250 milligrams. I start immediately the infusion at the fixed rate, the 60 milligram per hour. And this steady state concentration will not change, will be kept. You can calculate the other way using this equation CSS times PD, which is 10 times 25, will give you the same result. So once you follow this method, the concentration will be from the beginning almost stable at 10 milligram per hour. So you achieve rapidly target concentration. Now, kinetically, this is what happens. You are giving by two methods. You are giving IV bolus to achieve certain loading dose, and then you are also giving by IV infusion. You imagine you do the calculation for each one alone. IV bolus, the concentration, the loading dose, concentration resulting from loading dose will keep decreasing with time exponentially. There's one compartment model kinetics. And then we're talking about one compartment model drugs. If you, the infusion you start is causing an increase uh, in concentration. This is the equation of the infusion. This is the equation of the IV bolus loading dose. If you make a table and then you calculate CP note from the IV bolus and you keep calculating the time, the concentration with time. The other column, you calculate the concentration with time from the infusion given at certain rate. Make another third column and you plus levels from both types of administration. You find that the value is fixed. This is the total. The total is stable with time because the total is one is decreasing, but the other one is causing increase in concentration. The total, the sum is same. At infinity, at 5 half-lives or 7 half-lives, one is completely eliminated. This one reaches steady state. Okay? So the concentration from the infusion reaches steady state. This one is completely eliminated. So the total is always at steady state. This is confirmation to what we just said in the previous slide. Last example, drug was administered by continuous IV infusion at a rate of 0, 60 milligram per hour. A bolus dose of 50 milligram was started at the same time. Calculate plasma drug concentration 1 hour after starting the infusion, knowing that 0.17 K is 0.17 hour. The power minus 1 VD is 25 liters. So here I have infusion rate, I have loading dose, started at the same time. Calculate plasma drug concentration 1 hour after starting infusion. So we'll apply the calculation. 50 the gram. How much will be the resulting concentration? Then it will be dose divided by volume of distribution times E to the E exponent of negative K. So CP node is dose by volume distribution, 350 divided by 25 liters, 350 milligrams, times E exponent of
I'm
negative
sorry,
k times
doctor. We have
the
class right
time.
now.
Yeah, this is
So
the
is
final,
it
the
okay
final
if
one.
we stop here?
Okay, I keep recording and then you can go. It's only 1 minute. So here the concentration is equal to, resulting from the bolus dose is equal to 11.8 milligram per liter. From the infusion, we will follow the equation of the infusions. Then infusion rate divided by K times Ct times 1 minus exponent of negative Kt. We replace the values to give 2.21. Concentration at this time point is equal to both levels, 11.8 times plus 2.21 milligram per liter. If you do another calculation, how much would be the steady state concentration? Should be equal this amount in case that the concentration resulting from the 350 milligram is equal to the desired steady state concentration. So that's the end of the lecture. Thank you and have a good time.